In section 4, we're going to talk about solving right triangles. And when we talk about solving right triangles, we're talking about something specific. So when we say we're solving a right triangle, we want to find all missing angle measures and side lengths. In order to find our missing angle measures and side lengths, we're going to use two different theorems. The first being the triangle sum theorem. And the triangle sum theorem states that the angles in a triangle sum to 180 degrees. And then our second one is the Pythagorean theorem, which I hope you're all familiar with. And it is a squared plus b squared equals c squared, where a and b are the legs of the right triangle and c is the hypotenuse. So in order to solve a right triangle, there are some information that we have to be given. And we either need one side and one angle initially, or we need two sides. And without at least one of these requirements being met, we're not going to be able to solve our right triangle. So let's talk about the first case, where we're given one side and one angle. So we're first going to solve for x to find the length of CA. So in our triangle, we're given the angle of 42 degrees and we're given side AB is 6. So to solve for x, we have to set up a trig ratio. We have to set up the trig ratio a specific one. So if we label the sides of our right triangle, AB is the hypotenuse, x is the opposite side, and BC is the adjacent side. So we want to find the opposite side and are given the hypotenuse. So that means we're going to use the trig ratio of sine. So we know sine of our given angle 42 equals our opposite side x over our hypotenuse 6. And in order to solve for x, we have to get rid of the 6. So that means multiplying both sides by 6. So we get x equals 6 times sine of 42, which when we use our calculator, 6 times sine of 42 is going to give us that x is 4.01 approximately. And you want to make sure that your calculator is in degree mode since our angle was given in degrees. So and once we know x, we can finish solving the rest of our triangle, which we will do later. But right now we're just talking about that initial first case. So the second case is given two sides. So in order to solve this type of case, we have to introduce what may or may not be a new function. Some of you may already know it, others it may be new. And that's called the arc or inverse trig functions. And those are going to be sine inverse, cosine inverse, and tangent inverse. They're also sometimes called arc sine, arc cosine, and arc tangent. They mean the exact same thing, so no matter which way you see it written, they all represent the same thing. And the reason we use our arc or inverse trig functions is we use them to find the angle that gives our trig ratio. So they're used to find the angle that gives the trig ratio. So if you're given a trig ratio, the arc or inverse trig functions find the angle that would produce that trig ratio. So let's go ahead and look at some examples to see what that looks like. So we have sine of theta equals 3/5. So we know two sides of our triangle. So to figure out what angle would give that trig ratio, we're going to take the inverse sine of both sides. So to figure out which inverse function you use is whichever trig ratio you're given. So we're going to do sine inverse of both sides. So sine inverse of sine theta equals sine inverse of 3/5. Sine inverse and sine cancel, and we're left with theta on one side. And then to take the sine inverse of 3/5, you're going to use a calculator. It is a function on your calculator. You hit the button 3/5, and we get roughly 36.87 degrees. So for second example, we have tangent of theta equals 4.8. So to solve for theta, we take tangent inverse of both sides. And tangent inverse and tangent cancel. We're left with theta equals, and then when we do tangent inverse of 4.8, we're going to get about 78.23 degrees for theta. So it's very easy to use to solve for an angle measure in a right triangle given two sides. Let's go ahead and see how that's going to be used in an example. So in our triangle DEF, we want to solve for theta. So let's go ahead and label what sides we're given. 12 is the opposite side, so DE. EF is the adjacent side, and then DF is our hypotenuse. So we're given the opposite and adjacent to theta, so that is going to be the trig ratio of tangent. So tangent of theta equals 12/5. So to solve for theta, we take the tangent inverse of both sides. And we're left with theta equals 67.38 degrees. So let's go ahead and actually solve some right triangles. So just to review the definition that we're doing, so solving a right triangle is to find all missing angle measures and side lengths. And to do this, we're going to use the procedures in our previous problems, including the triangle sum theorem and the Pythagorean theorems to finish solving the problem. So we're going to use the following triangle ABC, and then we're going to do some examples. So our first example is given that theta is 51 degrees and C is 34, we want to solve the triangle. So I'm going to go ahead and label that information in our triangle. So theta is 51 degrees and C is 34. So we have two options to start off with. We can either solve for our missing angle beta, or we can solve for one of our side lengths first. And I'm going to go ahead and solve for our angle measure. So that's where the triangle sum theorem comes in. We know that theta plus beta plus our 90-degree angle have to equal 180 degrees. And we're given that theta is 51. So 51 plus beta plus 90 equals 180. And beta is just another Greek letter we can use to represent a missing angle. So if I do 90 plus 51, we're going to get beta plus 141 equals 180, and then subtract 141, and beta is 39 degrees. So that's one piece of information. Now that all that's left is to find our missing side lengths. So we can either solve for A or B first. It doesn't matter. Just depends on which trig ratio you want to use. So if we label our sides, side BC is the opposite side, and side AC is the adjacent, and side AB is the hypotenuse. So I'm going to go ahead and solve for A first. It doesn't really matter which one. So opposite over hypotenuse is sine. So sine of 51 equals A over 34. So to solve for A, we're going to multiply both sides by 34. So A equals 34 times sine of 51, which means A is approximately 26.42. And now the last thing we need to do is solve for B. And instead of using the Pythagorean theorem, I'm going to go ahead and use another trig ratio. And I'm doing that because we had to round to find A. 26.42 is not the exact length of A, it's an approximation. So we want to use exact values to find missing information. So I'm going to use another trig ratio to find B, and then I'm going to actually use cosine. So that means cosine of 51 equals B over 34. So to solve for B, we're going to multiply both sides by 34, and we get B equals 34 times cosine of 51, and that gives us a length of 21.4. And I may have gotten the exact same answer if I'd used the Pythagorean theorem. I may have gotten something a little bit different. We want to try to be as exact as possible when we're solving a right triangle. So we want to use exact answers. So our second example says that given A is 5.3, and C is 9.8, we're going to solve the triangle. So I'm going to relabel my picture. So A is 5.3 and C is 9.8. So because I'm given two angle measures to start out, two side lengths to start out, we're going to actually use the Pythagorean theorem first. So Pythagorean theorem, a squared plus b squared equals c squared. And I'm going to go ahead and, since our sides are a, b, and c, just plug in for the letter I'm given. So we know 5.3 squared plus b squared has to equal 9.8 squared. 5.3 squared is 28.09 plus b squared equals 9.8 squared, which is 96.04. Subtract 28.09. We get b squared equals 67.95. Take the square root, and b equals about 8.24. And again, not an exact answer, it is an approximation. So now we want to go ahead and solve for our angle measures. So we're going to set up the trig ratio that involves A and C. So if I go back up to my picture, if we want to solve for theta first, so we're solving for theta. A is the opposite side and C is the hypotenuse, which means in order to the trig ratio we're given, opposite over hypotenuse, is sine. So we know sine of theta equals 5.3 over 9.8. And in order to solve for sine, we take the sine inverse of both sides. And we get theta equals 32.74 degrees. Now I want to solve for beta. I could use the triangle sum theorem, but kind of very similar to how in the last example we didn't want to use the Pythagorean theorem when we rounded for a, we want to do the same thing here. Because we rounded to find theta, we don't want to round again when we find beta. So if we go back up to our picture, and if we're now solving for beta, 5.3a is now the adjacent side, c is still the hypotenuse. So when I set up the trig ratio, I'm actually going to use cosine. So we know cosine of beta equals 5.3 over 9.8. To solve for beta, we're going to take the cosine inverse of both sides. And we get beta equals 57.26 degrees. And again, I probably would have gotten the exact same answer if I'd used the triangle sum theorem, but just to be on the safe side, we're going to be exact in our answer. So let's do one last example in an application type problem. So in our problem, we have a person standing on top of a building that is 1,200 feet high. We want to know the angle of depression the person has to look down at to see a car that is parked 100 feet away from the building. So in application problems, it's always a good idea to draw a rough sketch of what you're given. So my building is 1,200 feet tall. I'm standing on the top of the building and I'm looking down at a car. And my car is not going to look very good because I can't draw. And this car is 100 feet from the building. So we want the angle of depression, which is, if you remember from geometry, comes from when you look straight out. So this is theta, which means equivalently in our picture, theta is going to fall, if you remember, the line going straight out is going to be parallel to our ground. So alternate interior angle. So the angle created from the car looking up to the top of the building is the same as the angle of depression looking from the top of the building down to the car. So it is not actually the angle inside our right triangle. So we want to set up the ratio based off our angle theta. So 1,200 is the side opposite and 100 is our side adjacent. So we're going to set up the tangent ratio. So tangent of theta is going to equal 1,200 over 100, which if I simplify, that gives me tangent of theta equals 12. So to solve for theta, we take the tangent inverse of both sides. So that gives me that theta equals 85.24 degrees.